Imagine a world where you could control your phone, your computer, maybe even a prosthetic limb,
Mm,
and communicate complex ideas, but without lifting a finger, pressing anything, or saying a word.
yeah.
What if just your intention could become the command?
It really does sound like science fiction, doesn't it? But, that's exactly the kind of cutting-edge tech we're digging into today. It's this fascinating, rapidly evolving field of surface electromyography, sEMG for short.
Okay, sEMG. Let's unpack that. So this deep dive is all about this technology. It's non-invasive, right? It senses and interprets the tiny electrical signals from your muscles.
That's the core idea. Often it's a device you wear, maybe in your wrist or forearm,
Gotcha.
and it basically listens to those muscle activation signals. It's trying to create a direct line, you could say, from your body signals to digital commands.
So our mission today is really to break down how sEMG works, look at the pretty big challenges researchers are facing,
Definitely challenges.
and explore some of the really incredible ways this technology is already starting to change things. Human-computer interaction, rehabilitation, even just, daily life stuff. We've got some great insights from the research we looked at.
Yeah, there's some really compelling stuff out there.
So let's start with the basics. When we talk about sEMG, what are we really talking about? What's the fundamental concept?
Okay, so picture a device, usually non-invasive, like we said, maybe like a smartwatch or an armband.
Right.
It's packed with sensors that are super sensitive to the electrical activity your muscles naturally produce when they, contract.
Okay.
It then takes those signals and interprets them to be used as inputs for a computer or a phone or a prosthesis. It forms what we call a human-computer interface, an HCI.
Human-computer interface.
Yeah.
So your muscles are basically talking to your devices.
In a way, yes.
Mhm.
That's a good way to put it.
And the big promise here, at least from what we've seen in the sources, is this idea of on-the-go control. Meaning you could operate devices with simple, easy gestures, really expressive inputs, without having to stop and look at a screen or fumble with the keyboard.
Exactly. Making that interaction seamless, almost invisible. That's the goal.
Okay.
And the research really talks about two main ways, two core concepts for how this control actually works in practice. Discrete control and continuous control.
Yeah.
They tackle different kinds of interaction.
All right, let's break down discrete control first. Am I getting this right? It takes a whole gesture, like a flick of the wrist or a tap,
Yeah, dynamic movement.
and treats that entire sequence as one single input, which then triggers one specific action or command.
That's spot on. The whole evolution of the gesture leads to one single output. It's what researchers often call a many-to-one mapping.
Many to one. Okay.
Yeah, lots of data points from the muscle signals during the gesture boil down to one command. So maybe a quick wrist swipe dismisses that annoying phone call,
Oh, yeah.
or a subtle double tap, maybe your thumb and index finger, silences your morning alarm without you even opening your eyes.
Ooh, I like that one.
Or you could use tiny directional thumb swipes, almost like drawing little arrows in the air, to guide a game character, replacing keys entirely.
That sounds incredibly intuitive, like a secret little language just between you and your tech.
It has that potential, definitely.
So how does continuous control stack up against that? What's different?
Continuous control is, well, it's more about constant fluid adjustments. Instead of one gesture equals one command, the system is continuously making predictions, usually at really small, fixed time steps.
Okay, constantly predicting.
Right. This is the kind of approach that's actually been commercialized already for controlling powered prostheses.
Oh, okay.
It allows for those really smooth, ongoing adjustments. Like, think about subtly changing the grip force of a prosthetic hand as you pick something delicate up.
Right, micro adjustment.
Exactly. It's more like a one-to-one mapping. One little window of muscle data translates directly into one immediate small output adjustment.
That makes sense. And for the discrete control, the research mentions some specific algorithms. Things like, let me see, majority vote LDA, dynamic time warping, LSTM. Using features like RMS and MAV, what are these actually doing?
Yeah, those are some of the key techniques. You can think of them as different strategies or computational tools the system uses to make sense of those complex muscle signals.
Okay.
So dynamic time warping, for instance, is really good at recognizing patterns even if they're performed at slightly different speeds. Sometimes you do a gesture faster, sometimes slower.
Right, handles variability.
Exactly. And then things like LSEMs, long short-term memory networks, they're a type of neural network that's excellent at understanding sequences and remembering what happened earlier in the signal, because a gesture isn't static, and it unfolds over time.
Got it. So they understand the timing and the sequence of the muscle firing.
Precisely. They're kind of the brains behind making accurate predictions from that messy biological data. Root mean square and mean absolute value, the RMS and MAV you mentioned, those are ways to quantify the amount of muscle activity in a little time window. They're features the algorithms use.
Okay, that clarifies things. Now, the potential is obviously huge, but let's be real. Getting these sEMG systems to work reliably, especially, outside a pristine lab, that seems incredibly hard. The research talks a lot about a data dilemma.
Oh, absolutely. That's a major, major theme. One of the fundamental problems has historically been just data scarcity.
Not enough data.
Not nearly enough, especially diverse data. Think about it. Recruiting people, bringing them into a lab, carefully placing electrodes, recording consistent gestures. It's a huge amount of work.
Yeah.
A real experimental burden.
Yeah.
So historically, studies use relatively small numbers of participants. We saw examples where even recent fancy neural networks trained on data from just, say, 11 people, they only achieved around 68% accuracy for cross-user continuous control.
68%. That's not great if you want something commercially viable for everyone.
Not even close. And that really highlights the core issue. Getting a model trained on one group of people to work well, right out of the box on someone completely new, that's the cross-user hurdle.
The plug-and-play problem.
Exactly. And making that leap is incredibly difficult with limited data. We saw one study that found to get really high accuracy, like over 90%, for what they call zero-shot cross-user models.
Meaning models that work on new users without any specific data from that new user.
Correct. To get that working well, they needed data from 150 subjects, and each subject had to perform each gesture 30 times.
Wow, 150 subjects, 30 reps. That's a lot more data collection.
It's a huge jump in scale. And then you have groups like Critro Labs, now part of Meta, suggesting they might need data from as many as, get this, 4,800 users to properly train zero-shot models, just for recognizing simple thumb swipes reliably across everyone.
4,800. That's staggering. It really puts the data challenge into perspective.
It really does. It shows the scale needed for true universality.
And then there's this other issue, the gap between how well things work offline versus online.
Right. The online versus offline performance gap.
What's going on there?
Well, the research suggests there's only a sort of moderate correlation between the accuracy you measure in an offline test, like classifying pre-recorded gestures,
Okay.
and how well the system actually performs when a real person is using it in real time, trying to achieve a goal, what they call user-in-the-loop control.
Why that difference?
Because real users don't just perform perfect static gestures like in training, they adapt. They subtly change how they contract their muscles. They modulate their effort to get the device to do what they want. These real-world patterns can be quite different from the clean training data.
So the way we use it changes the signals it sees.
Precisely. And that leads to another point these systems are, and the research uses this phrase, quite susceptible to confounding factors.
Like what? What kind of factors?
Oh, lots of things. Even a tiny shift in where the armband sits on your arm.
Right.
Or, electrical noise from other devices nearby, sweat changing the skin's conductivity, muscle fatigue over time. All these things can introduce errors, sometimes large errors.
So achieving robust performance when someone's actually using it requires a lot of training, both for the system and the user.
Exactly. There's often an extensive training burden mentioned to get reliable online performance.
And that brings us to the electrode themselves. You mentioned placement shifting. Why are they so tricky?
Well, especially with high-density sEMG systems, the ones with lots of electrodes packed closely together.
Yeah.
They're incredibly sensitive to exactly where each electrode is relative to the muscle underneath. Even tiny shifts may be caused by the muscle itself contracting or your skin moving. That can throw off the signal pattern significantly.
Okay, so very sensitive to position.
Very. And then there's just signal quality in general. It can be compromised by noise, like we said, but also things like your skin condition that day, how much you're sweating. Muscle fatigue changes the signal too. So it really requires meticulous placement and often frequent adjustments to maintain good signal quality.
Man, it sounds like a minefield of potential problems. Data scarcity, cross-user issues, online versus offline gap, sensitivity to everything.
It is challenging, no doubt about it.
So given all that, how are researchers starting to break through these barriers? What's changing? What are the new approaches with data and algorithms?
Well, the good news is there's a clear recognition of this general lack of data being a bottleneck.
Okay.
So a huge push now is towards collecting and, importantly, releasing large-scale, publicly available data sets. That's seen as a crucial direction for the whole field.
More data, better data.
Exactly. And we're seeing some really impressive examples pop up in the research we looked at.
Like what?
Well, there's one called EMG EPN 612. That one's public. Has data from 612 participants doing 6 simple gestures using the Myo armband, which is a popular early device.
600 participants. That's way more than 11.
A big step up. And there are others, really important benchmark data sets like NINA-Pro, Capgemini, the UCI EMG dataset, Heiser, Flexware HD. Many of these include data collected over multiple sessions, which is key for study and long-term use. Some use high-density electrodes.
Okay, so building the resources.
Yeah, and some are really specialized. There's one called ADSE, focused on sequential gestures, specifically drawing Arabic numerals in the air. They built it because there wasn't much data for that kind of sequential task.
Interesting niche.
And then there's the Delta dataset. That one's particularly noteworthy. It's multi-day, multi-subject, collected over several months, and even includes data from a participant with limb absence.
Wow, over months.
Yeah, it's designed to be a benchmark for studying long-term control, especially with dry electrodes, and seeing how well systems handle those day-to-day shifts in the signals. Data distribution shifts, they call it.
That sounds incredibly valuable for testing robustness.
It really is. And it's not just about sEMG and isolation anymore either. Some new data sets are multimodal.
Meaning they combine sEMG with other sensor data?
Exactly. Like K2-MUSE combines sEMG with kinematic data, the limb is moving, and even ultrasound images of the muscles.
Ultrasound too.
Yeah. And another, AVE speech, combines sEMG from facial muscles with audio and video of the lips for recognizing Mandarin speech. It's about giving the AI more context, more pieces of the puzzle to understand the user's intent.
A more holistic view. Makes sense. So bigger, better, more diverse data is one part of the solution. What about the algorithms? How are they getting smarter?
Well, this is where the power of deep learning really comes into play. It's making a massive difference.
So,
one major shift is moving away from handcrafted features. That's where engineers used to have to manually figure out which aspects of the sEMG signal were important for recognizing a gesture, like the RMS or MAV we mentioned earlier.
okay, the old way.
The old way. Now, with deep neural networks, especially convolutional neural networks, CNNs,
Right.
we're moving towards feature learning. The network itself automatically learns the most relevant patterns and features directly from the raw sEMG data. It figures out what's important.
So you let the AI do the hard work of figuring out the signal patterns.
Essentially, yes. And it often finds more complex and effective patterns than humans could easily define. Deep learning is also being used for things like signal restoration.
Restoring lost signals? How does that work?
Yeah, pretty cool stuff. One study used a specific type of CNN model, a UNet framework, to actually reconstruct missing data points in high-density sEMG signals. Maybe an electrode temporarily lost contact or was noisy, and they showed it significantly improved accuracy metrics, like reducing the error of the RMSE and increasing the R-squared value, which measures how well the reconstruction matches the original. It makes the data more complete and reliable.
That sounds super useful for dealing with those real-world signal quality issues.
Definitely. And researchers are developing highly specialized network architectures too, like the Spatiotemporal Feature Extraction Network, STFNN.
Okay, STFAN. What's special about that?
It's designed specifically for sequential sEMG signals, like drawing or gestures that unfold over time. It has modules to analyze both the spatial information, where the activity is happening across the electrodes, and the temporal information, how that activity changes over the sequence.
So it understands both space and time in the muscle signals.
Right. It tries to get a deeper understanding of those dynamic movements.
And you mentioned LSTMs earlier.
Yes. Recurrent neural networks, RNNs, and particularly LSTMs, are proving really effective. The research consistently shows they're great at modeling those temporal dependencies.
How one part of the signal relates to the parts before it.
Exactly. Which is crucial for things like continuous control or recognizing gestures online as they happen, or even interpreting something like air writing. They often outperform older, more conventional machine learning methods for these tasks.
Okay. And what about transfer learning? That came up too.
Transfer learning is a really powerful concept. The basic idea is that you can take a model trained on one task or data set, maybe a very large general one, and then adapt or fine-tune it for a new related task, often using much less new data.
So you leverage the knowledge it already gained?
Precisely. You could say, pre-train a model on thousands of hours of general muscle signals, and then fine-tune it relatively quickly for a specific user's gestures, or even adapt it to help detect signs of a condition like Parkinson's disease from their sEMG patterns. It makes models more adaptable and data efficient.
That sounds incredibly useful for personalization. And for dealing with those long-term changes, I think incremental learning was mentioned.
Yes, incremental learning is absolutely key for long-term robustness.
Hmm.
This is a way for the model to continuously update itself as new data comes in.
So it learns on the fly.
Kind of, yeah. It can sequentially incorporate new training samples without having to retrain from scratch every time. This allows it to adapt to those shifts in signal patterns. We talked about the armband moving slightly, the user getting tired, changes over days or weeks.
Adapting to the user and the situation over time.
Exactly. One study showed a system using incremental learning achieved a really high recognition rate, like 96.5%, even after multiple updates dealing with data shifts across days.
Wow.
Which was way better than just trying to use a model trained on day 1 for data from day 10, where performance had dropped dramatically to like 64%.
Huge difference.
And interestingly, the incremental approach even slightly outperformed a model trained on all the data collected over all days at once, while being much, much faster to update, like 10 seconds versus over a minute.
Faster and better adapted. That seems like a win-win for practical use.
It really does. It points towards systems that can genuinely learn and adapt with the user over the long haul.
Okay, one more technique mentioned was sensor fusion, combining sEMG with other things.
Right. The idea here is that sEMG alone, while powerful, has limitations. But you combine it with other sensors.
Like accelerometers, IMUs.
Yeah, accelerometers or inertial measurement units to track motion, or even tiny PZT sensors that can detect vibrations or pressure changes on the skin, sometimes data gloves for detailed hand posture, or even EEG to get brain activity signals.
So you layer different types of information.
Exactly. You get a richer, more complete picture of the user's movement and intent. This fusion often leads to more robust and accurate systems because if one sensor's signal is noisy or ambiguous, the others can help compensate.
Makes total sense. More data streams, more robust interpretation. So with all these advances, bigger data sets, smarter deep learning, adaptation with incremental learning, sensor fusion, how is sEMG actually being used now? How is it transforming lives or opening up new possibilities in the real world?
Well, probably the most profound impact we're seeing is in prosthetics and rehabilitation.
Okay.
sEMG is enabling much more intuitive, much more precise control of robotic prosthetic limbs. We're moving beyond the older methods where maybe flexing one muscle moved the hand open, another closed it.
Right, very basic control.
It's very basic. Now, users can achieve control over multiple movements simultaneously, sometimes even independent control of individual prosthetic fingers. This drastically reduces the sort of delays and the unnatural feeling of using a prosthesis for everyday tasks.
That sounds like a massive improvement in functionality, genuinely life-changing for amputees.
It really is. And the research also highlights development of things like modular sEMG systems, easier to customize, and these really interesting soft, robotic, interactive training platforms.
That's so robotics.
Yeah, using things like elastic artificial muscles. These platforms give users biofeedback while they practice. They capture really detailed muscle activation data, and they're designed so amputees can potentially do effective training right from their own home.
Wow, home training platforms. That's great for accessibility.
Definitely. And it's not just about the tech. It's about tackling the biological challenges, too. New approaches are specifically addressing those neuromuscular changes that happen in a residual limb over time, like muscle fibers shifting position.
Right, the body adapts.
The body adapts, and the systems need to adapt, too. These training programs, often combined with adaptive algorithms, are showing great results. We saw one example where an amputee participant's control accuracy jumped from around 58% to over 78% after just 10 training sessions.
That's a huge improvement in a short time.
It is. And beyond just performance, there's a psychological benefit too. Users report feeling more comfortable, more accepting of the prosthesis because it feels more responsive, more like an extension of themselves.
That feeling of control must be incredibly important.
Crucial. And sEMG isn't just for limb loss. It's being applied in broader rehab too. For instance, knee rehabilitation. There's a data set called KneePad with data from patients doing exercises like squats and leg extensions.
Oh.
The sEMG data helps automatically assess their posture and identify common mistakes, almost like having a virtual physio guiding them. It's also being studied extensively for understanding and potentially aiding recovery from motor impairments after stroke or spinal cord injuries.
Yeah. So really broad applications in health and recovery, but the uses go beyond the purely physical, right? What about communication?
Absolutely. Silent communication is a really exciting area. Research is exploring sEMG for recognizing sign language. One study proposed a framework using sEMG plus accelerometers for Chinese Sign Language, achieving accuracy over 96% for the specific coded gestures they used.
96% accuracy for sign language. Wow. And silent speech.
Yes, silent speech recognition. This involves picking up the tiny muscle signals from your face, jaw, neck, even your tongue sometimes when you articulate words silently, just mouthing them.
Uh-huh.
Systems are combining these sEMG signals with maybe audio snippets if there's any sound, or video of the lip movements. This can work even in really noisy places where speaking aloud is difficult, or in situations where you need silence.
Like that library or concert example, discrete communication.
Exactly. There's even work on wearable systems using sEMG plus those PZT vibration sensors to identify silent mouth movements in real time.
That feels very futuristic, which leads right into just general human-computer interaction, making it more intuitive.
Definitely. And some of the results are startling. One study managed to achieve almost 91% character-level accuracy in reconstructing text that people were typing on a keyboard,
Okay.
using only the sEMG signals from their forearms. Not looking at the keyboard, just the muscle activity.
Wait, typing just from forearm muscle signals?
Essentially, yes. They use the keyboard presses to get the labels for the muscle patterns, recording over 148,000 gestures from regular typists. It points towards truly hands-free text input someday.
That's mind-blowing. Almost 81% accuracy just from the forearm. Okay. And what about simpler device control?
Yeah, those simple wrist gestures we talked about earlier, like the
Yeah.
ones in the EMG EPN612 dataset. They're being used to select commands for things like robotic arms or even to fly simulated devices like a tandem helicopter in experiments.
So gesture control for complex systems.
Right, and even things like user authentication, using unique patterns of muscle activation as a way to unlock your devices, like a biometric password.
A muscular signature. Interesting. What else?
Driver monitoring is another area. Researchers are using sEMG, often combined with other physiological sensors, to study driver behavior.
Oh, so.
By designing specific driving tasks, accelerate here, change lanes now, make this turn, they can record the corresponding physiological signals, including muscle activity related to steering, braking, accelerating. The goal is to understand the driver's state, maybe to detect fatigue or distraction very early.
Ah, for safety systems?
Potentially, yes.
Okay.
And finally, fitness and sports. There's a system called MOT, which is wireless and low latency, designed for use in gyms.
Okay.
It's been successfully used to record detailed muscle activity during dynamic exercises. Dumbbell raises, lunges, jumps, squats, even with all the movement, noise, and impacts you get in a real workout, giving athletes and trainers much better data on which muscles are firing and how hard.
So from prosthetics to silent speech to typing to fitness, it's incredibly versatile.
It really is. The range of potential applications is just vast.
So wrapping this up, this deep dive really paints a picture of sEMG as a technology that, okay, it has some serious hurdles the data needs, the sensitivity,
What significant challenges?
but it's evolving incredibly fast. We're seeing these huge data collection efforts, really sophisticated AI like deep learning and these adaptive incremental learning approaches, plus more user-focused design.
Yeah, progress is tangible.
It really feels like it holds this immense promise for bridging that gap between what we intend to do and how we control our technology. Across just a dizzying number of fields, it feels like we're right on the edge of a totally new way of interacting with the digital world around us.
Absolutely. And maybe that leaves us with a final thought for you, the listener.
Mhm.
As we get better and better at translating these subtle, almost unconscious muscle signals into digital commands, how might that fundamentally change our relationship with technology? What new kinds of interaction, maybe even forms of, dare I say, direct human-machine symbiosis? What could emerge when our devices can literally feel our intentions before we even act?